So we've had an action potential, and we know that now that action potential is traveling down that axon through either myelinated or unmyelinated fibers. Now what happens next? Here we have the presynaptic terminal here, and the postsynaptic membrane, or postsynaptic neurons here. As you remember, this is the synaptic cleft in here. Now inside the presynaptic terminal we have these small vesicles that contain neurotransmitters. While this presynaptic terminal is at rest, these neurotransmitters tend to be away from the active zone, which is right at the membrane here, and bound to actin, which is a filament protein that we discussed earlier. We also have at the presynaptic terminal these voltage-gated calcium channels, and for the sake of simplicity, I've just added 2 here, but we understand that there are plenty more than that. Now what happens is that when that action potential reaches the presynaptic terminal through either a myelinated or an unmyelinated axon, voltage-gated calcium channels open up, and because we know that there's a higher concentration of calcium on the outside of the cell relative to the inside of the cell, calcium consequently starts to flood into the cell, into the presynaptic terminal. Through a number of intermediary steps that we won't go into here, calcium facilitates the undocking of these vesicles from actin through a number of mechanisms. And that vesicle is moved to the active zone, where it fuses with the cell membrane there and releases the neurotransmitters into the synaptic cleft here. And on this postsynaptic membrane here, you have a receptor, which actually looks nothing like this, but for simplicity's sake, you have this receptor that then binds the neurotransmitter. And because these neurotransmitters can be either excitatory, meaning that they lead to depolarization, or inhibitory, meaning that they lead to hyperpolarization of the membrane, they produce what's referred to as excitatory postsynaptic potentials or inhibitory postsynaptic potentials. And at the other end of the synaptic terminal, at the presynaptic terminal, this vesicle then is clipped off and taken back up into the presynaptic terminal to form another vesicle to be recycled. Now if you recall, these axodendritic, so that's axodendritic, meaning the axon is meeting the dendrite. So these axodendritic areas tend to be pretty far away from the axon hillock and the initiation site down here. So what we have is a number of axons terminating on these dendrites, more than I've even pictured here. Some will be bringing in positive ions. Some will be bringing in negative ions. And what we end up with at the action potential initiation site is the summation of all of these different ionic charges. Given sufficient positive charge coming in from these terminations, the membrane will become sufficiently depolarized at the level of the initiation site to trigger an action potential. For accuracy's sake, and because some of you will in fact be going into electrophysiology at some point in your neuroscience careers, I want to be clear that currents are not the same as the movement of charges. Specifically, a negative current can refer to either the movement of positive ions, ironically, out of the cell, or negative ions into the cell. So that's a negative current. So you would think of positive ions coming into the cell as being a positive current, but rather positive ions coming into the cell is an inward current which is actually a negative current. Now, because that's kind of a difficult concept to grasp, I'm not going to test you on that. So I will test you on the type of current, whether it's a sodium current or a potassium current, or whether positive ions are coming in, negative ions are going in. But I'm not going to test you on positive and negative currents per se. To sum up, we have the action potential that leads to the opening of voltage-gated calcium channels at the nerve terminal. 2. Calcium triggers the undocking of the neurotransmitter vesicles from the actin cytoskeleton. 3. The vesicles move to the active site. They fuse with the terminal membrane, open, and release their contents. 4. The vesicle's membrane is taken back up and recycled, and the neurotransmitter binds to the postsynaptic receptor. And 5, the binding of the neurotransmitter leads to a series of events that result in either an excitatory or an inhibitory postsynaptic potential, an EPSP or an IPSP. Remember those because you will hear those a lot. So that's excitatory postsynaptic potential, that's a depolarizing potential, or inhibitory postsynaptic potential, that's a hyperpolarizing potential. And that's the bare bones version of what happens in synaptic transmission. For the next video, we'll talk about neurotransmitters and some of their effects.